Okay, so yesterday towards the end we were discussing the alignment of the replica code that the receiver generates internally with the incoming code. In this context, we will also see how better alignment of the replica code results in more silver range measurement accuracy. At this point, we will discuss only at the top level. We will come back to this later again when we talk about the receiver operating principles. So this white sequence is the incoming code for a given satellite, and the green shows the replica that the receiver generates. And the difference between the edges actually shows the alignment error or misalignment between the two. Now, to understand this, let's first define a term called code phase. Let's say this is the incoming code. We will first define a term called code phase, and we are going to use this term extensively in our subsequent discussion. So just like a carrier, sinusoidal carrier, which is cyclic in nature, code also has phase. Okay, so in case of the sinusoidal carrier, this is one cycle, and from the beginning of the cycle we can find the phase, carrier phase, or the phase of the signal, sinusoidal signal. So it varies from 0 to 2 pi, right? Similarly, in case of the code, there is a period. The pattern, the sequence of plus minus 1, this is plus 1 and this is minus 1. Sequence of plus minus 1s repeats after a certain time called the code period. So we are going to define the code period from the beginning. Let's say this is the beginning, this is the first chip. From the beginning, and you can take this first point anywhere, just like here, you can take this one, you can take this one, but from that point you have to consider the entire cycle. Similarly here, you just take one chip as the first chip, and then you have to consider capital N chips, because there are capital N chips. We assume that there are capital N chips in a code period. T denotes the code period. So we need to take one chip as the first chip, and that is the beginning of the code period. So the rising edge, this is the rising edge. So let's say this is the beginning of a code period, and from this point we have to consider N chips in time T. How do we define code phase? So let's consider this is one chip. Let's consider some arbitrary chip and a point on the chip. Let's assume that this is the LH chip. So this is the first chip and this is the LH chip. And we are interested in finding the code phase of this point A. So let's denote that CPA. So how many chips are there before this chip which has this point A? There are L-1 chips. L-1 chips are there. Each chip is of duration TC. TC is the chip width. Okay. And where does this point lie in the current chip? So let's say, let me draw this chip again. And this is the point A. So this distance from the rising edge of that chip, let's call this distance A, TC. and A is between 0 and 1. Okay, so here it is 0 and here it is 1. In between it has some value between 0 and 1. So I have written ATC. So this is the phase of this code phase of the point A, which is calculated from the beginning of a code period. And this is given in seconds because TC is in seconds. TC is the chip width. Similarly, we can also express this in terms of chips. What does it mean in terms of chips? Means one TC is actually one chip. So instead of expressing it in seconds, we can just do this. L minus 1 chips are there before the current chip which holds A plus A, small a. So this is represented in chips. When we multiply TC, which is the chip width in seconds, we get the code phase in seconds. When we remove TC, we just consider the chips and the fraction of the current chip, we get the code phase in chips. Okay. Now this is the code phase of this point A in the incoming code. Similarly, we have the replica code. The green shows the replica. So what is the code phase of this point? So this is time. So at the same point, what is the phase of the green? So let's show the green chip here. It is somewhere here. The same point at the same time instant is here, and let's call this B. So in case of green, the same point L minus 1 TC plus BTC. This is in seconds. Similarly, we can write it in chips, then it will be L minus 1 plus B. It will be in chips. So this is the code phase as per the green sequence at the same time instant. As for the white sequence, this is the code phase. What is the difference? The difference is actually the misalignment or the alignment error. And we call it code phase error. We denote it as tau. Code phase error tau is Cp minus. So let's call this Cp tilde. This is the code phase error or the misalignment, alignment error. Yesterday we talked about the correlation of the replica with the incoming code, and we discussed that when the correlation, so for different shifts of the replica code, we correlate it with the incoming code and find the correlation value, and the maximum of the correlation value is compared against the threshold. If it crosses the threshold, then we say that the signal is present, that satellite signal is present. Also, some other checks have to be done, which we will not discuss at this point. So basically, when a satellite is acquired, so we call this the satellite is acquired. When the satellite is acquired, we actually have this primary peak. This is the primary peak. So we discussed all this yesterday. We will not get into that. And this is the representation that we have when the primary peak is obtained. So we shifted the green backward and forward and found the alignment which gives the maximum correlation. And that is what is shown in this figure. So let's assume that this sequence of the green replica gives the maximum correlation. And the correlation value has crossed the threshold, so the satellite has been acquired. So here I am drawing the primary peak again. By the way, I missed this. This one is minus 1 by 1023. This, the magnitude of this line is minus 1 by 1023. So here I am showing the primary peak again. Let's say this is the threshold. Now the maximum correlation has crossed the threshold, satellite has been acquired, and then what happens? So that is the question. Let's assume that the green has been aligned perfectly with the white. So they match perfectly. So there is no misalignment. This indicates that the correlation value is actually here. So you are correlating the green with the white and finding the correlation value. So if there is no misalignment between green and white, it will lie here. But actually, there will always be some misalignment because of the presence of noise. In the correlation function, we have not considered the effect of noise, but noise will always be there in the incoming code because incoming code is taken from the incoming signal and incoming signal has noise. So we cannot ignore the effect of noise. Noise will always be there, and because of noise, there will be a misalignment between green and white. Now the question is, how much misalignment can we tolerate? So let's assume that there is some misalignment which is given by this one, tau. This one is Tc, this one is minus Tc. Now for the receiver to acquire this satellite, the correlation value has to be somewhere here. So for some other correlation, for some other alignment, it will be somewhere here. Otherwise, it will not acquire that satellite. So in general, we can say that the alignment between the green and white will always be here or within a chip. This is Tc. Tc is the chip width within a chip. So this is the case for a particular correlation peak. What about this correlation peak, which is narrower? So this is a narrower correlation. Of course, this Tc and this Tc are not the same. They are two different chips, different codes. So let's say this is CA code, and this I would not say PU, but let's for the sake of an example, let's consider PY code or some other code with a higher chipping rate. Higher chipping rate means Tc is 1 by chipping rate. Tc is the chip width, so it is 1 by chipping rate. Higher chipping rate means, of course, Tc will be small and the base of the correlation peak will be narrower. This is a narrower correlation peak. And again, the threshold is there. So for this particular code, the misalignment will only be this much. So it does not tolerate larger misalignment error. This tolerates higher misalignment. This does not tolerate higher misalignment, right? So from this we can say that in the case of the red correlation peak, alignment of the replica with the incoming code is more accurate. Right? And how was this possible? This was possible because red code has a higher chipping rate. And we discussed that higher chipping rate implies higher null to null bandwidth. And just now we found that higher chipping rate implies better alignment. So from this we have concluded that higher chipping rate results in better alignment. Fine. But how better alignment helps in getting better pseudo-range measurements? We know that pseudo-range is given by C times TU minus TT. TU is the TR minus TT. TR is the time of reception, TT is the time of transmission, C is the speed of light. And what is the magnitude of C? C is 299792458 meters per second. Now using the receiver clock, we get TR, time of reception. How about TT? The TT has obtained, TT is obtained from the navigation data and replica code. The navigation data bits are all time stamped. Okay, we can precisely find the time of the beginning of each bit. So from the navigation data, we actually get a coarse component of TT. And then see, the replica is aligned with the incoming code. So if alignment is good, we can consider the green sequence, the replica, as the incoming code, the code that was generated in the satellite, right? And when the code, carrier and navigation data were generated in the satellite, they are all time synchronized. So the rising edge of each chip of the code that was transmitted by the satellite was perfectly synchronized in time. So if we assume that the green is aligned with the white, meaning the green is actually what the satellite transmitted when the signal started from the satellite. Each chip is precisely synchronized. The beginning of each chip or any point, that point A on a particular chip had a particular time when it started from the satellite. Now we assume that the green is nothing but what the satellite transmitted, because the objective of the receiver is to align the green with the white. So if the better the alignment, the better would be the time that we derive from the chip, right? This is why it is very important to align the green with the white. And we have seen that using the red with narrower chips, with higher chipping rate, we can better align the replica with the incoming code. So if we better align the replica with the incoming code, later we'll see that this fine component, how we get this fine component. So don't worry about this fine component. And also the coarse one. So when we talk about the receiver operating principles, we'll see how we can get the coarse component and the fine component. For the time being, just note that the coarse component of the time of transmission is obtained from the navigation data, and there is a fine component which we derive from the replica code, because we assume that the replica is nothing but what the satellite transmitted. And this assumption is valid because the receiver tries to align the replica with the incoming. Now in this context, note that even a millisecond error can result in kilometer level inaccuracy. Why? Because we are multiplying c, speed of light, which is large. So if you make a millisecond error in calculating the time of transmission, it will result in kilometer level error in the sequence. So it's very important to perfectly align this replica with the incoming. We cannot tolerate even millisecond error here. Okay. So this explains how better alignment results in higher pseudo-range accuracy, and also how by using a higher chipping rate we can get better pseudo-range accuracy. This also partially explains to you why there were so many codes that were developed as part of GPS modernization. The objective was to improve the pseudo-range measurement accuracy. Any question, anything that you could not follow and want me to explain again? Understanding this is important. So you understand how better alignment, at least to a certain extent, how better alignment results in better pseudo-range accuracy, higher pseudo-range accuracy, and how by using the chipping rate we can achieve better alignment. Next, I want to talk about false acquisition quickly. See, in this case, we are matching the replica with the incoming and checking whether for certain shift the maximum correlation crosses the threshold or not. Now, generally, when the satellite signal is not present, when we match the replica with the incoming signal, if the satellite is not present, we will get the secondary peaks, which are not supposed to cross the threshold. Ideally, the secondary peaks are not supposed to cross. See, these are all secondary peaks. They are not supposed to cross the threshold. But this is an ideal case. Here we did not consider the effect of noise. Now, because of noise, it may be possible that a secondary peak crosses the threshold, because noise can amplify it or attenuate it. If the noise present in the incoming signal amplifies it, then it can cross the threshold. If it crosses the threshold and receiver declares that the satellite is acquired, that results in false acquisition because that satellite signal is not present, but the receiver says that the satellite has been acquired because a secondary peak has crossed the threshold due to noise amplification. This is called false acquisition. Now we do not want false acquisition because a satellite will be falsely acquired and the receiver will allocate some resources for further processing to that satellite, which is not desirable. Later it will conclude that the satellite is not acquired. So unnecessarily it will allocate resources for that particular satellite. So this is not desirable. How can we reduce the chances of false acquisition? By making these secondary peaks smaller. How can we make the secondary peak smaller? Now pay attention to the denominator of the peak. It is 1023. Here I have shown you for the CA code. We know that there are 1023 chips in a code period. If the code period had been longer, we would have more number of chips and the peak would have been diminished. We would have got lower values. So one way to avoid false acquisition is to increase the code period. So this partially explains to you why there are efforts for introducing longer codes. So longer codes can reduce the chances of false acquisition. Okay. So we understand partially why different codes They are developed with higher chipping rates and longer periods. Okay. So now we understand that this primary peak is important, right? We are not interested in the secondary peaks. We are actually interested in the primary peak. And this is 1, the maximum magnitude is 1. Yesterday we discussed why this is 1. And here at the base it is minus 1 by 1023 in case of CA code, which is the simplest of all. So this will be roughly about 1 by 1000, so 0.001, and this is 1. Okay. Next, we are going to make some approximation to the primary peak and define a mathematical function for it. So what we will do is this magnitude, which is roughly minus 0.001, will be approximated to be 0. Okay, because this is 1 and this is minus 0.001, very small. So we approximate this to be 0, and then we just have a triangular function as the primary peak. And we are going to use that triangular function in all the subsequent discussions. We ignored the secondary peaks, we just considered the primary peak in all the subsequent discussion, because we know that the green has to be within this peak for further processing. Satellite has been acquired, and for further processing the primary peak is of importance. We are not bothered about the secondary peaks anymore. This is tau. This will say Tc. This is minus Tc. When we write it in seconds, when we write it in chips or express it in chips, this is 1, this is minus 1, this is 1. Okay, and the corresponding mathematical function is given like this. When tau is in in seconds. In this particular case, where tau is in chips, we just have this. Okay. Any question? You understand how the primary peak has been approximated as a triangular function like this? Understanding this is important. That's why I'm asking again. If you do not understand, ask me. Now suppose the satellite has been acquired. We know that the green is within a chip of the white incoming code. But that accuracy is not sufficient. As I told you, we require a very accurate estimate of the time of transmission. So the receiver, after acquiring a satellite, continuously tries to align the green with the white perfectly. And this continuous process is called tracking. Later, when we talk about the receiver operating principles, we will see that it uses some feedback control loops to perform tracking. So tracking is a continuous process. So after acquisition, tracking begins. We'll come back to this later. After acquisition, tracking begins. When the receiver continuously tries to better align the replica code with the incoming code, and it uses some feedback control loops to do that. We'll not get into the 8 feedback control loops now. To get into feedback control, we need to talk about many other things which we'll discuss under receiver operating principles. Okay. But at this point, I want you to know that to accomplish this task, the receiver needs to generate 3 replica codes. It's not that just one replica code is generated by the receiver. In fact, to align one replica with the incoming, it requires 3 replica codes. Okay. They are called early, prompt, and late. So each satellite has to be tracked. In the conventional architecture, each satellite is separately tracked. Okay, and for each satellite, 3 replica codes are generated. They are called early, prompt, and late. So let's say this is the incoming code, and we are interested in a particular chip. Okay, so let's pick the midpoint of this chip for simplicity, and time elapses in this direction. So at the current time, let's say this point has come. So these sides have already gone. This is the current point. Now let's consider the prompt replica. So receiver actually tries to align the prompt with the incoming. Okay. And assume that the prompt is perfectly aligned. So at this point, in the prompt chip also, this is the midpoint. Let's assume that prompt is perfectly aligned. Okay. Now two more replica codes are generated. One is called early, another is called late. So early is actually shifted ahead. Blue is early. It is showing the same chip in the early code. So this, since early is shifted ahead, the same point of the early code has already passed. That's why I am showing it on the left side. It is shifted ahead. Okay, and how much it is shifted ahead? Let's say b by 2. So you take the corresponding points of prompt and early and find the difference between them in terms of chips or seconds. Here I have written it in chips. Okay, d by 2. That's why I did not multiply TC. So this is what the corresponding chip of the early code looks. Then we need to show late. The late code is actually shifted late. So for the late code, the same point would occur later. So this is the midpoint of the late, and this shift is again d by 2. So early is shifted ahead, and late is shifted behind. Okay. Now the receiver tries to match the prompt with the incoming. It correlates the prompt with the incoming. In this particular case, the prompt is aligned with the incoming. So the correlation value will be here. So this is the correlation, primary correlation peak. So this side it is 1, this side it is -1, and I am showing it in chips. In this particular case, the green is perfectly aligned with the white. So if you correlate the green with the white, you get this one. I'll use a different color. You get this one because the green is perfectly aligned. How about prompt and late? So if you correlate prompt with the incoming, you will get this point. If you correlate late with the incoming, you will get this point. Okay. Now what if the green is not aligned? If the green is not aligned, means you will not get this point. When you correlate the green with the white, you will get, depending on the error, whether it is positive or negative, you will get some point this side. Let's assume a positive error. You will get this point this side. Now, since early and left are shifted with respect to the prompt, their correlation values will also change. So, for this particular case, this will be the correlation value of the late, and this will be the correlation value of the early. In case when the green was aligned with the white, both early and late, they have the same correlation value. But when the prompt or the green is not aligned, is misaligned, then early and late do not have the same correlation value. So the objective of the receiver is to compare the correlation of late and early and see whether they are equal or not. So basically in the feedback control loop, the receiver intelligently tries to zero the difference between late and early. If it can make the difference between the two zero, meaning these yellow points, then automatically the green will be aligned with white. Okay. If you do not understand, ask me. And the receiver has to do it continuously, because once it is aligned does not mean it will remain aligned in the future also. Okay, so it needs to continuously do it. Okay, and that's why we call it tracking. So it's like it is tracking the incoming code. Any question? You understand what I said? You understand the objective of early, prompt, and late?
Yes, ma'am.
Okay. So that's all about the signal structure. Next, we are going to discuss the effects of the atmosphere on GNSS signals. In the pseudo-range equation, we write rho as c times Tr minus Tt. C is the speed of light. In a vacuum. Here is the receive time. We also call it time of reception. And Tt is the transmit time. Now, if you consider the path from the satellite till the, let's say the receiver is on the ground, okay, here the receiver is, which receives signal from the satellite. For about 95 to 97% of the distance, the signal travels in a vacuum, where you can use the magnitude of speed of light I gave earlier, 299792458 meters per second. For the rest, 3 to 5%, it travels through the Earth's atmosphere. Okay. Now, at about 1,000 kilometers from the surface of Earth, the signal enters a layer of charged particles called the ionosphere. And at about 40 kilometers above the Earth's surface, it enters a medium of neutral gaseous molecules called the troposphere. Okay. Now, both ionosphere and troposphere, as far as GNSS signals are concerned, we do not identify other layers of the atmosphere. Okay, ionosphere and troposphere, two layers. Both ionosphere and troposphere change the propagation speed of the signal through refraction. Okay. As a result, the signal reaches the receiver at a different time instant. Had there been no atmosphere, the signal would have traveled at the speed of light in a vacuum and reached the receiver at some time. Because of the presence of the ionosphere and troposphere, which change the speed of propagation through refraction, the time of reception is changed. Okay. So under this topic, we are going to talk about the ionospheric error and tropospheric error. Okay, and how the receiver can eliminate them, either fully or partially. Okay, that's all for today. We'll continue this discussion next week. You have your project presentation in the evening from 5 to 7. I'll send you the meeting link before 5 p.m. Okay, any question? Fine, you can leave now.